doing some work on a pruning algorithm which uses logical constraints to generate pruned models which are more robust to adversarial attack. So this is joint work with Rob and Katja, who just introduced themselves, at Heriot-Watt, my two supervisors, and then I'm a PhD student at Heriot-Watt, also in the LAIV group. So neural networks are increasingly being moved onto edge computing devices and smart sensors in order to reduce latency and save on bandwidth. So with the ever-increasing size of neural networks, then comes the question, how do we fit these large networks onto resource-constrained devices, such as FPGAs, mobile phones, and special-purpose robotics hardware? So one solution to doing this is to compress neural networks. So there's two kind of big families of methods for compression that are used a lot, and one of them is quantization. So that's where we reduce the precision of parameters in a network. So for example, here you can see we can have some weight matrix and we take floating point values and we're able to reduce them down to integers. This can be done all the way down to binary values with quite small loss in accuracy. Then we've got another family of compression methods called pruning. So this is where, rather than reducing the precision, we actually just remove parameters completely from the network. So then we ended up with a model with far fewer parameters in it. So we end up with a smaller model, and if compilers and hardware are able to leverage this, you should have a network that uses less memory, less computation, less energy, and so it should be able to fit easier onto smaller devices. So we're going to be focusing on pruning today. Pruning methods are able to kind of greatly reduce the number of parameters in a network without having much of an impact on their accuracy. So I've kind of got three example models that we'll be looking at today. So one of them is ResNet, trained on CIFAR 100, which is just a data set with 100 different classes of images. And then VGG, again, trained on the same data set. And then we've got a much simpler model, LINET, which is trained on the German road sign dataset. So as you can see, along the x-axis, we've got the percentage of parameters that we've pruned from the network, and then we've got the accuracy along the y-axis. So you kind of have to read from right to left. As we remove parameters from the network, you're able to get down to around 40% maybe of parameters remaining without a massive difference in accuracy, and then past around 75%, there's like a massive drop in accuracy once we've kind of pruned too many parameters from our network. Yeah, so pruning, we're able to kind of massively reduce the size of networks without having much of an impact on the accuracy. But today we're going to be talking also about the robustness of networks. So I'm sure we've all seen similar images to this a bunch of times. You've got some input to a neural network. In this case, we've got the character 4 from the MNIST dataset. Some perturbation is applied to this image, so some adversarial noise. For example, here we've just got some gray pixels in the background. This will then cause our model to misclassify this character 4 that any human observer would see as a 4 as a 6 instead. So what does this mean for pruned models? There's not a massive amount of literature on this. One thing we've seen is that there can actually be a slight increase in robustness from applying pruning to either just the input before actually giving the input to the model, or by applying pruning to the fully connected layers only of a model. So when we're dealing with images, we usually deal with convolutional neural networks. So we have some layers that apply filters to images, and then we have some layers that are just kind of like standard, a long list of neurons with weights connecting them. And if you apply the pruning only to these fully connected layers, which make up quite a small percentage of convolutional networks usually, we can have a slight increase in robustness. However, if we prune either all of the layers in a network, a convolutional network, or we prune only the convolutional layers, we actually see like a substantial decrease in the network's robustness, which isn't ideal. We'd hope to be able to prune all layer types in a network in order to be able to actually prune quite a high proportion of them. So yeah, it's important to make sure we're pruning all layer types in a network, and we want to kind of work towards an algorithm that can do this without this massive decrease in robustness. Another thing worth noting, because there's people in this group that are interested in verification, pruning can actually also be used And if you're able to preserve these properties during the pruning, then you can verify the smaller method, the smaller network, sorry, rather than having to verify this larger model. Okay. Yeah, so now if we just look at the robustness of pruned models, we're using a benchmark pruning method here that we're going to be kind of measuring our algorithm against. So this method prunes the convolutional and the fully connected layers from a network, and just using again these same three models from the last graph, we see that there is this kind of decrease in robustness, especially you can see that quite well with the blue line with the ResNet model. So we want to kind of be able to prune models without seeing this kind of big decrease in the robustness. Cool. So the key results of the algorithm I'm presenting today are that we're able to prune 75% of parameters from ResNet, trained on CIFAR 100 dataset. And the model that we train using this algorithm is 29.6% more robust than the benchmark, and there's a 0% loss in accuracy. And then also, we're able to prune between 9 and 75% of parameters from VGG. In this case, the models that are pruned with the robust, logically constrained pruning algorithm actually have higher robustness than even the original unpruned model. So we can see some improvements, not just with respect to the benchmark, but with respect to kind of a model that hasn't been pruned yet. Okay, so I'll just quickly go through how pruning works. When we train a neural network, we just do this by minimizing some loss function. So we're looking for values for W, which are the parameters in our network, such that we can minimize this loss, which is dependent on our dataset and our weights. And this is usually done iteratively using gradient descent. With pruning, it's very similar. So we're trying to minimize the loss function, but it has a scaling coefficient included. So we've just got some constant lambda and then the L naught norm of our weight matrix W. So L naught is just the number of non-zero elements. So this will be the number of non-zero parameters in our network. In practice, this is done by iteratively measuring the saliency of the parameters in our network. So for an individual parameter in our network, the saliency is just the change in our loss caused by setting that parameter to 0. And then if we take a Taylor expansion on the right-hand side, you can see that this is easily measured just using gradients of our loss function. So starting from a full unpruned network, we remove parameters with the lowest saliency in the network. So as you can see, some of these connections have been removed from the network. And then if a neuron no longer has any connections to or from it, it no longer has any impact on the network itself. And then we retrain, and then again, we remove the parameters with the lowest saliency. So we're kind of iteratively getting a smaller and smaller network every single time. So we have these two steps, and we have our value n prune, which is the number of parameters that we remove at each pruning step. And then we have n train, which is the number of training iterations performed between each pruning step. So we repeat these two steps. We prune, we retrain, we prune, we retrain until we get a network that is the size we're happy with. Value, and any weight whose magnitude is smaller than this threshold is just removed from the network. So this is much easier to calculate, so it's going to be much faster, and there's not a massive difference in the accuracy you get from networks using this method rather than gradients of the loss function. So that's why it's so widely used. However, we're interested in using this kind of original method of saliency, where you take gradients of loss function, because we're able to kind of leverage using some fancy loss function that contains some information that will hopefully result in robust networks.
Sorry, Kirsty, I think your sound cut out at the very start of the sentence for everyone. What was the second method of pruning, which didn't use the loss function?
Oh, the threshold one, sorry. Hi, can you hear me now?
Yes, yeah, it's good now. You sound good.
Okay. I was just mentioning that in most kind of pruning literature, people use this threshold method where they just take some threshold value, and then any weight whose magnitude is smaller than this threshold value is removed from the network. So this is a much simpler method, and it's easier to calculate, so it's quicker, and people use it because there's not a massive difference in the accuracy you get on the networks using this method rather than actually using the gradients to loss function, which is a bit more complex.
Great, thanks.
Okay, cool. Yeah, but we're going to use the gradients of the loss function for this algorithm because we're able to kind of leverage using constraints in our loss function because we're interested in the robustness of the pruned models as well as just the accuracy. Cool, so how do we do this? We take inspiration from robust training methods, one method in particular called DL2 that we've talked about in this seminar before, but I'll just explain how it goes for those who haven't read the paper. Rather than minimizing some standard loss function, you're going to minimize some constraint-aware loss function, which is dependent not just on the dataset and the weights, but also on some constraint phi. So our constraint-aware loss function is just the sum of the standard loss and then some weighted term. And this weighted term is going to be made up of the average for our constraint term for every individual input in the data set. So for each input in the data set, we're going to measure our constraint. And then if our constraint is satisfied, this term is going to be 0. And if our constraint is not satisfied, this term is going to be equal to 1. So then we take an average for all of the inputs in the data set, and we get some value that we then add to our standard loss function. So our loss is now dependent not just on the accuracy of the network, but also on how well our network adheres to this constraint. Cool. So we now need to pick a constraint to use, and there's some discrepancy on what exactly the definition of robustness is in across the literature, and we tried a few different definitions, and there's one in particular that worked really well for us. So this is where we measure for one input in the data set, we measure how robust our network is for a ball which is drawn around the radius around this input. So if we have some input, for example here 7 from the MNIST data set, we draw a radius r around this input in the input space to our network, and then we kind of sample the space around our input. So you can see here we've got our number 7, and then we've got some images which are very similar to that number but with some slight perturbation, some slight adversarial noise. And then there's 2 cases. So if all of the points that we've sampled are also classified as a 7, our constraint holds. And if one or more points sampled is misclassified, then that means our constraint no longer holds. So how do we actually measure this? We take our dataset D, and that's made up of a bunch of inputs, small d. And for each of these inputs D, we draw a radius r around our input. We then kind of sample this area, and if there's a misclassification, our constraint does not hold. If there's no misclassification, our constraint holds. So from here, we're able to get some percentage value for the robustness of our network. So the robustness of our network for the data set is simply the percentage of points where we've sampled within this radius and we did not get a misclassification. So the way that we're actually doing this is we got some code from Marco, who's in this group as well, and we use the FGSM attack to find a point within radius r of our original input, and then we either get a misclassification or we don't get a misclassification, and then we're able to use this as our constraint. Cool. So finally, how do we get from a pre-trained, unpruned model to a pruned model? The first step is to do our retraining. So we update all of the weights in our network by minimizing this constraint-aware loss function. And then the next step is to measure the saliency using, again, the constraint-aware loss function for each weight in the network. We repeat this as many times, a predefined number of times. And then once we've done enough retraining, we calculate the average saliency for each parameter in the network. So we're going to have a bunch of saliency measures from all of the retraining steps. We want to calculate the average, and then we use this to find the end-pruned parameters which have the lowest saliency, and we remove these from the network. So at this point, we have a network which is more pruned than the network that was put in, and we can output a pruned model, and then we can also return back to the first step and keep going. So we're iteratively kind of creating a pruned model at each different level of pruning. So we're using this constraint-aware loss not only for the retraining, but also for the saliency measures. So the choice of which parameters to remove, as well as the retraining, which is going to train the remaining parameters to try and compensate for the parameters that we've removed. Both these calculations are done with our constraint. Cool. So now we're going to use two of our models, the ResNet model in CIFAR 100 and the LANet model in GTSRB, to kind of see how this impacts our network's accuracy and robustness. So I've got two graphs here. In blue, we have the baseline model, which is just pruning without using the constraints in the loss function. And then in orange and green, we've just got two different weights for this weighted term in our loss. And as you can see, there's not a massive difference in the accuracy across using these different methods. So usually there's this trade-off between accuracy and robustness. And using this method, you can see there's not a massive difference in the accuracies when we're using our constraint pruning algorithm or when we're just using a standard pruning algorithm. Cool. One thing that you notice, I'll actually just go back. So we have this massive drop in accuracy when you get to a certain level of pruning. And for some models, it happens very suddenly. And we want to kind of look into why this is happening. And one good example of this is just using, again, this really simple LANet model on the MNIST data set. I've got some confusion matrices here, and I've kind of turned them into heat maps to try and make it easier to look at them. So basically, when you're looking at a confusion matrix, if all of the values along the diagonal are very high, so here, if we've got black squares along the diagonal, that means that all inputs for one of the classes are being output as the correct class. So we've got here digits from 0 to 9. So if you've got black squares along the diagonal, that means that everything's being classed correctly. And then you would want to have kind of the light gray across the rest of the network, across the rest of the classes, sorry. So I've got 4 examples here. We've got a completely unpruned model. We've got a model with 75% of parameters pruned, 95%, and then 99%. And as you can see, up to 75% of parameters pruned, we've still got the same confusion matrix from the unpruned model. But then at 95% of parameters, we see something a bit different happening. So you can see for classes 1, 3, 7, and 8, there's a reasonable amount of inputs being classed as these classes. However, a lot of these are false positives, so they're not along the diagonal, which kind of implies that these are misclassifications. And then for some classes, so in this case, we've got 0, 2, 4, 5, 6, and 9, very few classes are actually being, very few inputs, sorry, are actually being classified as these classes by our network. So it kind of shows that when you get past a certain level of pruning, certain classes in the network are now inaccessible. And if we take it to the extreme case, you see that for 99% of parameters pruned, only the class 5 is actually being output by the network. So no matter what you input into the network, it's always going to classify it as a 5. So we want to kind of take this and then measure for different levels of pruning, what is the percentage of class.
Sorry, Kirsty, I think you've cut out again. I'm not sure if you're back yet.
class data set. As you can see, when you get past around 20% of parameters remaining, we see this massive increase in the number of classes that are inaccessible. But up until that point, the percentage of inaccessible classes, or the deterioration, stays pretty constant at 0. And if we look at ResNet, again, it stays at 0, and it doesn't start to deteriorate until a much lower number. So using our logically constrained pruning algorithm, there's actually not really any difference in the deterioration compared to the baseline. Cool. And then finally, we want to look at the robustness of the networks using our algorithm and then using the baseline algorithm. So in blue, we've got the baseline, and then orange, we have a smaller weight, and green, we have a larger weight. So the higher the weight of the constraint term in the loss function, the better robustness you end up with. And overall, we get better robustness than the baseline. But one interesting thing that actually happens, so if we look first at the GTSRB, so between around 9% of parameters having been pruned and 75%, you see that you've actually got better robustness here than we had with the original unpruned model. And then you can kind of see this again with the ResNet. So between around, I think it's around 20 to around 50, you've actually got better robustness than you had for the original unpruned model. This is because for the unpruned model, we've just taken a trained model, trained benchmark models off the internet, and when we actually use the robust training during the retraining steps of the pruning algorithm, this is actually improving on the robustness compared to the original model. Yeah. So in conclusion, we're able to produce models which are more robust than when pruned just with some standard pruning algorithm, and there's a negligible loss in the accuracy when compared to this. So in some cases, we end up with pruned models that are actually a bit more robust than the original unpruned model. And then we also looked at the deterioration of classes in a network, which makes some classes inaccessible. And again, there wasn't much of a difference when using our algorithm or a standard algorithm. Cool. So if you follow this link, you can find the code, more graphs, and the workshop paper that I submitted last week or the week before. So thanks for listening, everyone. And I guess if there's any questions.
Thank you, Kirsty.